Hello everyone and welcome to the presentation about supporting task switching with reinforcement learning. My name is Alexander Lingler and I'm a second year PhD student of the University of Applied Science in Upper Austria. I had the pleasure to do this work with my colleagues Dinara Talypova, Jussi Jokinen, Antti Oulasvirta and Philipp Wintersberger. Let's start right away with the motivation of this work. We are here in the research area of multitasking. And like you probably have experienced by your own, during a regular working day, we are exposed to different kinds of interruptions and notifications. And all these interruptions come with some costs, like higher stress level or higher error rate. For instance, while I was preparing this work, I got 3 phone calls, 10 notifications from Windows, and of course, I also was checking my phone to just procrastinate. And some of these notifications and interruptions were important, but many were not. And now the question is, how could we deal with this multitasking environment and this kind of interruptions? But before we're talking about a solution, we should briefly talk about multitasking, which can be defined as a continuum reaching from concurrent to sequential. Concurrent would mean talking while driving, and a sequential one would writing a paper and then answering an email. But we also should conceptually look how we switch between tasks and the involved costs. So currently I'm focusing on task 1. Then this task 1 is interrupted by a second task. And as you can see, there is this kind of gap between those tasks, which can be described by an interruption lag, where I have to rehearse and clean up my current mental representation of the first task, that I then can attend the second task. Then after certain times, the second task ends, and then I want to resume to the first task. And also again, I have here this resumption lag, which just describes the time and effort to restore my mental representation from the primarily interrupted task. And what I also have to say is that usually these task switches work the best at task boundaries. For instance, when I'm reading a paragraph or a text, then after the end of the paragraph, it would be a good time to switch the task, because it's then easy for me to reattend this task. Since we now know about multitasking, we can look at solutions which are already out there. And there are, for instance, this kind of attention management systems, which computationally seek to balance users' need for minimal disruptions and the application's need to deliver information. And now the question is how this system can accomplish that. And there are different strategies. For instance, interruption timing. So like I've told you, one strategy would be to just switch at task boundaries. Attention management system could try to detect these boundaries and then switch to another task. Another way would be to check the availability status of the human, which can be described based on different features, like how concentrated I am and so on. And the attention management system could also provide resumption cues, helping the human to reattend to the formerly interrupted task. Then the question is, why do attention management systems hardly exist? Most of the current solutions work with supervised learning, and as we know, supervised learning again relies on training data, but unfortunately it's hard to collect the training data, and it's also a time-consuming process. Furthermore, these supervised learning approaches use handcrafted classifiers, often with different layers which are highly complex, and the problem with those solutions is that they maybe work for one problem, but not for all problems. So therefore, they are often task dependent. And since also for the training data collection approach, we need a lot of training data, and therefore often we just aggregate the training set among a huge ground of participants, and therefore we cannot adapt to individuals in these solutions. And yeah, but at the end, there's the most important point. Since we are working with training data and it's a supervised learning approach, we need human labels from experts. But in our scenario, where we, for instance, want to find the opportune moment for a task switch, it could be the case that just the human expert does not really know the perfect strategy. Therefore, we cannot learn or get the superhuman performance. Therefore, we came up with another solution using reinforcement learning instead. In reinforcement learning, we have an agent interacting with an environment by observing the current state of the environment. And according to this state, the agent will then perform an action which should maximize a certain reward function. And hopefully we can then achieve our objective. And since we are using reinforcement learning, we do not need to collect the training data beforehand, and therefore we are more task independent, and we do not need this hard and time-consuming training data collection process. But the most important point is, since we are not relying on human expert, we can now learn this superhuman performance. And therefore we claim with our solution that we can design a reinforcement learning-based attention management system that improves human performance without the need of any training data. Therefore, to prove our claim, we implemented a balancing game where you have to balance two balls on two platforms, but you can only control one platform at a time, and the supervisor decides for you when to attempt a certain task. And the difficulty level will increase after a certain time. Therefore, this task is highly visual and cognitive demanding, like, for instance, driving a car, but with the advantage that we can easily measure the performance by the seconds both balls stay on their respective platform. Okay, then let us have a look at our reinforcement learning solution. Now we have to answer a question, namely, how can we train such agents? Normally, we should use humans playing the balancing game to train the supervisor, but unfortunately we need too many training steps, and therefore this wouldn't be feasible in practice. Therefore, we could use techniques like imitation learning, but we decided to use a theory called computational rationality, where we again include an additional environment, namely one agent trying to solve this balancing game, but we include human bounds and constraints into this environment. Therefore, this agent cannot really observe the true state of the environment, but only a belief state. Therefore, there's this kind of internal representation. So, for instance, also we human cannot really perceive 100% accurately our environment. Therefore, we also have an internal representation about the environment. And the cool thing about this approach is that we can use different parameters to model diverse capabilities by setting a strong value, for instance, for these constraints. And you will see we will do this in this work. So, for instance, we have a normal distribution, and depending on the standard deviation, this constraint is either strong or not that strong. Therefore, for our architecture, we have to distinguish between a training phase and an evaluation phase. In the training phase, we use our internal environment. Therefore, we include human constraints into the training phase of our supervisor. And as you can see, we have here this pattern ball and this white ball, and the white ball is the belief state of the ball, and the pattern ball is the true ball position. And based on that, so for instance, at the moment the left platform is active, we can model a forgetting of the true ball position for the currently inactive platform, which can be seen on the right side. And then for the evaluation, we do not have to use our training environment anymore. We just use humans instead of the model. And since the supervisor was trained based on our model mimicking humans, now this agent should also work for real humans. The next step, we have to define how we can update the belief state. In our case, we just discretized the platform into bins, and the belief state just describes the probability that the ball is inside of a certain bin. Therefore, we are dealing with a probability distribution here. On the bottom, you can see this formula, how we update the belief state of S prime, just describing that the ball is in state S prime. And therefore, we have to calculate the sum of all probabilities of the states multiplied that with the chance that we get to our target state S prime from the state by performing action A. And as you can see, we also have this kind of observation function here, and this observation function is used in case that we are currently looking at the active platform, and in that case we want to weight the true ball position stronger compared to all the other platforms, since we want to get the belief state and the true ball position in sync if we are observing the currently active platform. I also want to briefly talk about the transition probability P, where we use a normal distribution of the ball velocities to calculate the chance that we get from state S to our target state S prime. On the right side, you can see the algorithm, how we update the belief state. Please have a look by yourself. But you will realize after a certain time that we can update the belief state of all the different bins independent of all the other bins. Therefore, this step is perfectly parallelizable, and we can calculate this update of the belief state at runtime. On this slide, you can see a visualization of the belief state update. Currently, the blue platform is inactive, and as you can see, the belief and the true ball position strongly differ over time. And when the platform gets active again, those two positions get back in sync. Based on that, we can model the reaction time, which is related to the time needed to internally update our representation of the current environment. Finally, we can talk about the results of our user study. Before that, we have to talk about the design. We used a quantitative lab experiment in 4 different conditions. 2 times our supervisor, 1 time trained with our cognitive model, and 1 time trained with an unconstrained model. Therefore, this model learned a superhuman performance. Then our participants also used a self-chosen task switching strategy. Therefore, they had to switch between the platform based on the shoulder buttons. And we also included a notification mode where we do not automatically switch to the currently inactive task, but before that there will be a notification, and then the participant has to switch by themselves. And this user study consists of 43 participants, 30 male, 12 female, and mainly students and university staff. Regarding the results of the performance, you can see on the right side a box plot describing that the participants who were supported by the supervisor, trained by the cognitive model, outperformed any other condition. And we have to say here that it was essential to use computational rationality here, since the supervisor trained by the unconstrained model performed quite poor. This can be explained that even if the supervisor randomly switches between the task, the model without any constraints has the ability to fix any position because there aren't any reaction times involved. We also measured the switching behavior and found some interesting results here. When the participants switch by themselves, they choose for a more cautious strategy compared to the condition where they were supported by our supervisor, who also switched for more difficult situations. For instance, when the ball has a high velocity, the distance to the center is large, and so on. And this, to a certain extent, counters the theory that switches are only a good idea at task boundaries. And according to our survey, although these situations seem to be more stressful, the participants perceived the switching condition where they were supported by a supervisor less cognitively demanding and physically demanding. Finally, I want to conclude this presentation with the key takeaways of our experiments. So we were able to design a reinforcement learning-based attention management system that improved human performance. And one key aspect was that we had to use computational rationality to train our supervisor. And as you have seen on the last slide, our system provokes fast-paced performance, but without influencing the human perceived workload. And we hope to inspire you to also try this combination of reinforcement learning and computational rationality to integrally consider human resources and limitations into this kind of systems. And I want to conclude with further call for downloading and extending our software, implementing additional tasks, or playing around with the cognitive model to further improve performance and research of cooperative attention management systems. With that, I say thank you very much, and I'm looking forward to answer your questions soon. Bye.